Lesson 19 examines the possible instability of steel beams. The instability limit states may prevent the steel beam from reaching the yielding limit state or the plastic moment M sub P. Instability or buckling in a beam can take three forms, very similar to a column. There is global buckling and what is called lateral torsional buckling or LTB. There is also local buckling, either flange local buckling or FLB, and web local buckling or WLB. Again, local buckling occurs due to slender elements in the cross section. Lateral torsional buckling occurs due to the instability of the beam's compression flange. If the compression flange is unsupported or unbraced along a portion of its length, it will try to buckle, much like a column. For the beam shown in this slide, the top flange is in compression under the action of the load. Now looking at the compression flange, which has a rectangular cross-section, its weak axis would be the 1-1 axis. However, the flange is continuously attached to the web, which prevents it from buckling about this axis. However, if the stress is high enough and the compression flange is not sufficiently laterally braced, the flange may buckle about its strong axis or the 2-2 axis. As the compression flange buckles laterally, it will try to bring the rest of the cross-section with it. However, the bottom flange is in tension, which means it is very stiff and has no desire to go along with the top flange. As a consequence, the entire cross-section will also twist, hence the name lateral torsional buckling. Note the vertical deflection of the cross-section is the normal deflection expected under gravity loads. Lateral torsional buckling can occur under certain conditions prior to the beam reaching the plastic moment. A given cross-section resists lateral torsional buckling with two types of stiffnesses: its weak axis bending stiffness and its torsional stiffness. Note that short, stocky cross-sections are more resistant to lateral torsional buckling than tall, slender cross-sections. Lateral torsional buckling, or LTB, can be prevented in several ways. One is to provide lateral bracing, much in the way we could brace a column at mid-height to increase the buckling capacity about the y-axis. If a floor beam supports a concrete deck, the deck will fully laterally brace the top compression flange. There needs to be some type of connection between the top of the beam and the deck, which there usually is in the form of shear connectors. Lateral bracing can also occur at intervals or discrete points. This may take the form of other beams framing into the beam under consideration, or bracing members dedicated to stabilizing the compression flange. As we will see in Module 9, another way to prevent lateral torsional buckling is to reduce the load on the beam. Module 9 will provide design calculations for a reduced moment capacity as a function of the unbraced length L sub B. The calculated moment capacity is based on the stress distribution present at the time of lateral torsional buckling. In the design of beams, we must determine if and how the individual member is laterally supported. The distance between bracing points is known as the unbraced length, L sub B. The longer the unbraced length, the more susceptible the beam is to lateral torsional buckling. As a minimum, the member will be supported laterally at the ends of the member by the supports. The unbraced length is then the entire length of the beam. If lateral bracing of the compression flange is provided at mid-span, indicated by the small x in the drawing, the unbraced length becomes half the length of the beam. This reduces the unbraced length by half and will result in a significant increase in the moment capacity, much like bracing a column at mid-height. Additional discrete points of lateral bracing will increase the moment capacity further. The elements of a beam, the flanges and the web, are also susceptible to local buckling, similar to a column. Therefore, local buckling is another limit state that may prevent the development of the plastic moment capacity of a steel beam. Note that for a symmetrical cross-section, 1/2 of the web goes into compression. One must check both flange local buckling and web local buckling, similar to how it was done for columns. A W shape that is not susceptible to local buckling, meaning its slenderness ratios do not exceed the slenderness limits, is called a compact section. Therefore, assuming lateral torsional buckling is not an issue, these compact sections can reach a moment capacity defined by the plastic moment M sub P. This ends Lesson 19 and Module 8.